Hello, and here we are starting the last of the really big topics in pre-university physics. So this is electricity and magnetism, or electromagnetism, depending on how you want to describe it. And it's interesting because we've got these two different phenomena here, electricity and magnetism, which are actually inseparable. It's a single phenomenon of electromagnetism. So this is something that we're going to have to unpick as we're going through this topic. And the path that we're going to take through this, at least at a high level, looks relatively straightforward. We need to first of all get this picture of how, what are these two phenomena? Why have we got these two things, electricity and magnetism? Why are they inseparable? Why is it one thing with two faces? And I'm actually going to go through that in this video, at least to get a high level picture of the basic behavior which is behind electricity and magnetism. And then we're going to move on to the two main parts of this, the two main chunks of the topic. So we've got circuits, and then we've got stuff to do with electric and magnetic fields and the like. So circuits, this is the macroscopic side of electricity and magnetism. So really we're looking at current electricity. We're looking at the transfer of energy through the movement of charged particles. This has been completely revolutionary to the world. Scientific discovery that's then been taken advantage of in engineering. Everything that we do depends really on our knowledge and understanding and manipulation of electrical circuits. So really, really important. So we need to understand the behavior of circuits and then how we can engineer those circuits in order to achieve good outcomes in the world. So that's our macroscopic view, where we're just looking at things at a much more aggregated level. We're not looking at individual electrons or other charged particles. We're looking at them on aggregation. And then the other big chunk is then these electric and magnetic fields and the energy and the forces that are associated with these fields. So we're going to move down to the microscopic level. We're going to need to get this description of the behavior of matter that has electric charge. We covered some of this in the section on the structure of matter, looking at fundamental particles and how some of those fundamental particles behave as the electromagnetic interaction that they engage in. And this is then looking at the microscopic. Of course, we've got this typical split that I talk about every time we get to a new topic between classical and modern physics. So once again here we're going to be very much inside classical electromagnetism, as we are in all the other topics. Beginners in physics, we start in classical physics, and we can still get, as we do in all the other topics, some really good descriptions and predictive abilities out of classical physics. So that's the basic way that we're going to be dividing this up. But as I say, it's useful to get a picture, at least a basic understanding of the behavior which is underlying all of this. So that's what I'm going to start with now, is talking about this fundamental interaction that's got these two faces, this electric side and this magnetic side. So we've already seen in the section on structure of matter that we've got some matter engages in the electromagnetic interaction, just as you've got some matter that engages in the gravitational interaction. This is things that we say have got mass, they're affected by gravity. Things that we say have got electric charge engages in the electromagnetic interaction. So if you think back to our fundamental particles, the ones that got electric charge are the quarks, the leptons that aren't neutrinos, so the electron, the muon, the tau, and what else have you got? Oh yeah, the W bosons. So there's quite a few of them that have got this electric charge, and they're said to have electric charge because they engage in the electromagnetic interaction. The other thing that we saw with that, as shown in the Millikan experiment, is that electric charge is quantized. It comes in chunks. It's not like mass, where you can just, it's sort of this continuous range of values that mass can have. Yeah, electric charge is going up in multiples of the charge on the electron, this 1.6 times 10 to the minus 19 coulombs. I mean, I know that quarks have got fractions of that, but quarks don't exist in isolation. So once you've grouped them together into pairs or triplets, then you end up getting multiples of the charge on an electron. And of course, that is already mentioned as well with that electric charge is measured in coulombs. That's our unit of electric charge. It's the electrical charge equivalent of the kilogram. So we got a sort of match up there between coulombs and kilograms. So we've got all of that we've already covered about which particles have got these got this electric charge. Now, naturally, we're going to end up making a lot of comparisons to gravity as we're going through this. I mean, that is the interaction that we've already dealt with. We've done a lot of work, particularly in classical mechanics, on gravity. So it's natural when we start talking about another force, another set of fields and things like that we're going to make comparisons to gravitational fields and gravitational forces and such like. So we've already seen a few of the differences between them, because there are a lot of similarities, but there are also a lot of differences. So we've seen that we've got coulombs, although it's the electromagnetic equivalent of the kilogram in terms of measuring electric charge versus measuring mass, but we have got the difference that electric charge can be both positive and negative. So it can attract or repel. Gravity is only attractive, whereas this electromagnetic interaction can be attractive or repulsive. So that is a difference. We've also got the difference that electric charge is quantized. But we have a lot of similarities. In classical physics, we were describing, in classical mechanics, I should say, we were describing gravitational fields using Newton's law of gravitation. We talked about gravitational potential as being this energy per unit mass. That's what we were talking about for gravitational potential. Now we're going to be talking about something quite similar with electric potential, where we're now talking about energy per unit charge. So we've got this direct comparison that we can make here in terms of fields. So we've got potential fields. Again, we're making that distinction. Remember, we made that distinction before between potential and then potential energy. If we want to turn a gravitational potential into a gravitational potential energy, then we need an actual mass to turn up. So we can multiply the mass by the mass and then say how much energy that we've got left. So that turns our gravitational potential into our gravitational potential energy. We've got a similar thing here. The potential is this electric potential is abstracted away from a particular amount of charge. It's saying, okay, we've got a potential field, which is defined using this energy per unit charge. So we've got some field which exists. We've got various field lines. Let's say we've got a radial field around a central charge. Then we put some charge into the field, multiplied by the charge, and then we're getting the electric potential energy. So remember that difference there between potential and then the potential energy. So we've got the same process going on here that we had before in classical mechanics. We've got the same thing with gravitational field strength and electric field strength. So we spoke about gravitational field strength as being the force per unit mass. That's our gravitational field strength. And then for electric field strength, you can guess it, we're going to get our force per unit charge. So again, a direct comparison between the two things. And we'll be quantifying this mathematically later on, when we get onto the second big chunk of the topic, when we're looking at these electric fields and magnetic fields in more detail, we will quantify all of this mathematically. So we've got these similarities here where we're going to continually make this comparison of the similarities and differences between electromagnetic behavior and gravitational behavior. Right, so all of this though has been, you would have noticed, has all been very electric focused. Where's the magnetism in all of this? We haven't said anything about magnetism yet. Now, there isn't a magnetic charge equivalent to electric charge or mass or anything like that. We've got these fundamental properties of of matter, where we're saying, yeah, some matter has got electric charge. We don't say, yes, some matter has got magnetic charge. So where's the magnetism coming in then, if it isn't this basic property of matter? Well, magnetism is a result of moving electric charge. So, and this is where we get this inseparable relationship between electricity and magnetism. So if we've got some charge Q just sitting here in space, that's got an electric field around it. And then if we get that charge to move, so Q moves through space, we've now got a changing electric field. Now, one of the physical facts of the universe is that a changing electric field produces a changing magnetic field, which we denote with a B. And that changing magnetic field then produces a changing electric field. So we've got this loop going on here where it's just going round and round in circles, this perpetual cycle. Two fields that are interrelated, they're sustaining each other through their change. Changing electric field makes changing magnetic field, which makes changing electric field. So this initial disturbance of the moving electric charge, that initial disturbance then creates this perpetual cycle of oscillations. This is where an electromagnetic wave comes from. You think back to what we were talking about in the previous section on waves and oscillations. This is the underlying part of it, that you've got these two phenomena here on an electromagnetic wave that are sustaining each other. As one thing changes, it changes the other one, which then changes the first thing again. So this is the underlying sort of fabric of the universe, if you want to call it that. This is the behavior which we're trying to capture in all of this. It leads us towards Maxwell's equations. Maxwell's equations are the encapsulation of all of this, all of the behavior of electric charge and electric fields and magnetic fields. This is all described in Maxwell's equations. I'll do a video later on Maxwell's equations. I won't be able to go into them in an enormous amount of detail because the maths is far beyond what we can, well, maybe not far beyond, but it's certainly beyond what we cover before we go off to university. Maxwell's equations, those four equations, you could kind of look at them as being the benchmark of first year undergraduate physics learning. That if you can then understand and describe and explain Maxwell's equations, then you've got a reasonable first grasp on classical electromagnetism, if I can say the word. So I will say something about Maxwell's equations later on in a separate video. But yeah, we've now got this relationship here. So the electric field has got this just straight electric charge. If you've got a static electric charge, you get an electric field. But that doesn't come with a magnetic field. There is no magnetic charge which produces a magnetic field in the same way. So you have to have charge in motion in order to get a magnetic field. This is where, well, this is the foundation for magnets, isn't it? Well, as it would be, it's the foundation of all magnetism. But magnets, if you look at any atom, you've got electric charge in motion. You've got these electrons orbiting the nucleus of the atom. These electrons are in motion, so you've got changing electric fields. Those changing electric fields will then create a magnetic field, and the magnetic field that is created is then described using a dipole, as in it's got two poles, our north-south, as we talk about magnets, north-south. We've got monopoles for electric charge, as in we just got here's a positive charge, here's a negative charge. It's just a value of charge. There's no dipole, there's no distinction between a north and a south in a single electric charge, whereas in this manufactured magnetic charge, which is coming from the movement of electric charge, it comes as a dipole, it comes as a north-south. And then if we want to get a magnet, like an iron magnet, to actually go around picking stuff up, then what we need to be doing is aligning all of these north-souths. If everything is just in, higgledy-piggledy directions, then they're all going to cancel out as a macroscopic effect. But if we can align all of these, which is what is happening when we're creating a magnet, either deliberately by an electromagnet, if you pass electric current through there, we can align all of these dipoles. If you're rubbing another magnet against some iron, you can use it to align these dipoles. If it gets zapped by some lightning, then you can align them and then you get a magnet. So the magnetic effect is a consequence of this moving electric charge. But I think this is really important because I'm going to move on to circuits in the next video. And this is what's underlying how electric current is set up and can sustain, how we can actually propagate a current along a wire. Because to get a current to flow, we're getting this propagation of an electromagnetic field along the wire. We need an electromagnetic wave to propagate down the wire to make the charge carriers start moving, but the speed, the electric speed, is in the propagation of the field. It's not in the movement of the electrons. So having some kind of picture of this cycle, this interrelationship between electric effects and magnetic effects, if you've got that in your mind, then it can make it easier to get a picture of what's happening with electric current. So I'm going to leave that there as a basic description. At least we've got some things in our mind here that we're going to be drawing comparisons with gravity as we're going through this section to see the similarities and the differences, of which there are many of both. Excuse me. And we'll also be continually coming back to this interrelation, this inseparable relationship between electricity and magnetism in order to explain all these other behaviors. So keep those two ideas in your mind as we move forwards. So onwards to circuits.